So I'm gonna start by sharing the screen. All right, somebody else is coming in. Come on. All right, so this is what we'll be looking at today. The how the if what the effect is of varying the excitation current and how the machine is utilized for power factor correction. I sent the notes yesterday, so I hope you had a chance of reading it. All right, so this is what we'll be looking at today. Machine operating at different excitation currents, but we actually will be looking at it from the reverse end, where we actually will be changing the power factor for a particular machine and then see what happens with the excitation. So we'll be looking at that, and as I said before, we'll be looking at the power factor correction. All right, so to look at this particular effect, the effect of excitation, we're gonna be looking at it by use of an example. So we'll be looking at a three-phase wire-connected synchronous motor, which has a full load rating of 7.2 kilowatts at 0.5 power factor leading. Its synchronous reactance is that 4 ohm per phase, and RA is equal to 0. And we are asked to calculate the armature current, the excitation voltage, which is what we also call the generated voltage, and the field winding current. Now, remember before we spoke about the direct relationship between the field winding current and the AC excitation voltage or the induced EMF in the stator. So for this machine, EA is equal to 100 times the field winding current. All right, so we're asked to look at that first for 0.5 power factor. Then later on, we're going to be looking at it at different power factors, both leading and lagging. And for each case, we're going to be working out current, armature current, excitation, voltage, and field winding current. And then something that I want you to do, I will start it, but I will want you to finish it. We're going to look at the same calculations for the machine delivering half load. And later on, you will plot graphs of the excitation voltage versus the field winding current and the armature current versus the field winding current for both full load and half load. So you'll actually have two graphs, one for A, EA versus IF, and the other one for B, IA versus IF. But on each of the graphs now, you will have these values being plotted for full load and for half load. So you will see what we're talking about if you haven't read the notes yet. All right, so as usual, the calculations are fairly straightforward. We have been through some of them already. So this is your single phase equivalent circuit. Sorry, not single phase, but per phase equivalent circuit for this three phase Y connected synchronous motor. And so the impedance is basically the reactance, and that's equal to J4. And at 0.5 power factor leading, the angle is 60 degrees. All right, so we're asked to find the armature current, so you know that the input power to the stator would be coming in here, and this would be the armature current. So you can use this formula, stator, that input power to the stator is 7.2 times 10 to the 3 watts. Doing the calculation, IA works out to be 39.97, and the angle associated with it would be 60 degrees. All right. So again, you go through the calculations, and we work out what EA is. And EA is 270.63 at angle minus 17. And IF is EA divided by 100. So IF is 2.7 amps. And we do the same thing for 0.8. So again, we just substitute the values. And EA now works out to be 196.99 at angle minus 23. And IF is approximately 1.97. Unity, similar procedure. EA works out to be 144 and IF to 1.44. And then we go back through for lagging power factor now. So know that with the lagging power factor for the current, the angle is negative. So IA now becomes 24.98 at minus 36.87. Again, we substitute the values in the formula. And this time we get EA equal to 100 volts and IF to be 1 amp. And again for 0.5, and EA works out to be 82 and IF at 0.82. All right, so if we do the same calculation, yeah, sorry.
Morning, sir.
Morning.
Just clarifying something. So EA would be the equivalent to VF.
To VF? No. EA is the induced EMF in the stator.
Okay. But we can still use it to find IF.
Right, because there is a direct, for this machine, there is a direct relationship between A and IF. Here it is.
Oh, right.
EA is
Right.
equal to
Yes, sir.
100 IF.
Yes, sir. Thanks.
All right. You will see similar kind of relationship. So there is a linear relationship between EA and IF. You know, as you increase IF, you'll get more. So as you increase the field winding current, more flux will be produced. And as that flux rotating at synchronous speed cuts the stator windings, it induces more EMF in there, right? So you will find that as IF is increasing, the EA will also be increasing. So EA is an induced EMF on the stator windings, but note that the stator also has a supply voltage, the three-phase voltage supply connected to it also. So this is basically a kind of the induced EMF acts basically like a back EMF or a counter EMF to the supply voltage. Okay?
Yes, sir.
All right. All right, so we were getting now to the stage where the machine would be delivering half load. And half load means half of the its rated full load. So it's half of the 7.2 Let me let in somebody here. Half of the 7.2 kilowatts, so it's 3.6 kilowatts. All right, and we work out the currents for half load, and at a leading power factor of 60 degrees, IA would be equal to 19.99 at angle 60. And then EA works out to be 193, and IF, where's my mouse? And IF is 1.93. All right, so this is something now that I want you to continue as you get some time today to finish these calculations. So yeah, this is what I'm saying here. So you should perform the same calculations if the machine now delivers half load for the same kind of power factors that we had before. All right, and when you have done that, you should plot graphs of EA versus IF and IA versus IF for full load and half load on the same axis. So what that means is that here I'm plotting IA versus IF, and see I have a curve here for full load and a curve here for a partial load. So notice that they are on the same axes. So this is what I'm talking about when I want full load and half load on the same axes, right? And when you have done that, you should identify regions of overexcitation. I think you would have known what the definitions are for overexcitation and underexcitation. You can even indicate normal excitation also. All right, so this is what you should be doing. You should get two curves on the same axes for A and also for B. All right. So I did a tabulation of the results that we had. So here now you will see excitation changing. So the excitation current, the DC current, we see it increasing here from 0.82 up to 2.71. All right. And as it increases, we see IA changing and the power factor also changing. So here we have a lagging power factor at 0.82, but by the time we reach 1.44, it is unity power factor. And by the time we reach 2.71, we are at 0.5 leading. So what we are showing here is that if we vary the excitation, we can vary the power factor. All right, so that is the important thing that we want to know. You vary the excitation, you vary the power factor. All right, and then this table down here is used to plot this graph. All right, so you will be getting, so this will be the full load graph, and then you will be drawing, you will be plotting also the half load graph after you do the calculations for half load. All right. So this actually has the shape of a V. It probably look a little bit better here. So these are called the synchronous motor V curves. All right. And as you can see, they can give you some information as to what kind of current, field winding current can give you what kind of power factor. All right. So you would know that below a field winding current, below this value here, would be giving you lagging power factor, and above this value will be giving you leading power factor. So it's something you would want to know for your particular synchronous motor. All right, so let's get into power factor correction. All right, so normally factories utilizes a lot of electrical machinery, you know, mostly induction motors and other loads that require reactive power. Now, these are usually lagging power factor loads, and hence the power factor for our industrial plant can become very poor, right? Much lower than Unity, right? Now, having a low power factor is costly and inefficient. And I think you would have been introduced to that before when we did DRIVES 1, and we looked at power factor correction using the capacitor. Now we're going to be using another type of capacitor. All right. So because of the poor power factor and the poor efficiency, efforts are usually made to correct the power factor. Right. So there's also a cost implication as pointed out here. So if your power factor is very poor, you'll be paying more for your electricity. So you want to reduce that kind of cost. So efforts are made to correct the power factor. All right. This is usually done by applying some kind of equipment that supplies reactive power. And the synchronous motor is one such equipment. All right, so you see a drawing here. So the three-phase line is here. And this load here represents the factory. And then a synchronous motor here is connected to improve the power factor of the entire system now. So the load plus synchronous motor becomes the system. All right. So I want you to recall what we had just gone through a while ago, that the synchronous motor can be made to operate at lagging, unity, or leading power factor. So lagging power factor, IA lags VA. Leading, IA leads VA. All right. We're assuming that VA is our reference phasor. So for a leading power factor, when a machine operates as a leading power factor, at a leading power factor, it will supply reactive power to the machine, to the source, or to the system that it is connected to. All right. So here we're going to be doing a little proof of that. All right. So for when IA is leading, the phasor becomes IA angle theta. And if we consider the single phase or per phase power, then S is equal to VA times IA conjugate. So you would have remembered conjugate from maths, and the power system people would also be familiar with S is equal to VI conjugate. All right, so from maths, you can recall that the conjugate of an angle is the angle multiplied by -1. All right, so IA conjugate would be IA at angle minus theta. So S, which is equal to VA times IA, and V at angle 0, I at angle minus theta, will give me VA angle minus theta. Right? So for a leading power factor, the angle associated with S is a minus theta, minus power factor angle. All right. And if we take this up to the three-phase level, then the three-phase apparent power would be 3 times the per phase apparent power. Right? So for a balanced system, all the thetas would be the same. So it's 3 VA IA angle minus theta for a balanced three-phase system. And we usually assume that our three-phase machines, for this course, for DRIVES 1 and DRIVES 2, three-phase machines are considered to be balanced. All right, so for S is equal to VA IA angle minus theta, P is equal to minus JQ, right? So for a synchronous motor supplying leading power factor to its AC voltage source, S is equal to PM, so SM for motor, PM minus JQM. All right. So I want you to remember that now that the synchronous motor is actually a load, and this will show you that it's actually a load and the supply voltage also. Right? So it is a load that is connected to the voltage source. Now, a load that has a negative sign associated with its reactive power is in fact supplying reactive power to the voltage source or to the system to which it is connected. Let in somebody. I hear what somebody is saying here. Okay. All right, Mr. Green. Now, a load that supplies reactive power would be a capacitive load, right? And see, we have power triangle here. So this triangle here would be for a lagging power factor load. All right. And notice the similarity with the impedance triangle. For the same system, the angle theta would be the same for both the power and for the impedance. All right. So for a lagging power factor load, the triangle is this upper triangle. And for a leading power factor load, the triangle is the lower one here. Right. So the synchronous motor will be operating on the lower triangle, while the factory load would be operating on the upper triangle. And the factory load we consider to be a lagging power factor load. All right, so the synchronous motor, which is specifically built to supply reactive power to the voltage source or system to which it is connected, is considered to be is known as a synchronous condenser. All right, synchronous because it's rotating. Condenser is the old name for capacitors. All right, so the synchronous condenser supplies reactive power for power factor correction. And as it does that, it also improves the system voltages. All right, and I guess we have gone into that before, so you can probably dig up back your notes on those from drives 1. So the synchronous condenser is not connected to deliver a mechanical load. And it draws a small amount of real power, this PM, to supply its winding losses, core losses, and to overcome friction and windage. All right, so PM relatively small compared to the reactive power that is delivered. All right, this is something that I want you to do also when you have some spare time. I want you to prove that for a lagging power factor load, S is equal to P plus JQ. All right, and S would have a positive angle theta. All right, so you can start by looking at this. For a lagging power factor load, IA would be equal to IA angle minus theta. And then you can use that based on what we did before to show that S is equal to P plus JQ. All right, so that is something that I want you to do also. So every time you see something in red, it is something for you to do. All right, I might not call on you to ask for it now, but it probably will appear at some other time. Now let us look at an example of power factor correction using the synchronous motor. All right, so this factory has a 2000 kVA load at 0.5 power factor lagging. So it's very poor. And the synchronous motor is added to raise the power factor to 0.8 lagging. All right, the motor itself now will take a real power, the PM, of 100 kilowatts. And we're asked to determine the power factor and kVA rating of the motor. All right, so we'll get into that. So first we'll look at what the factory is doing. in terms of real and reactive power. So at point 8, at 0.45 power factor lagging, we can work out what the angle is. So this cos inverse 0.45 is to work out what the angle is. And when we work out the angle, I mean, I just do the calculation one time. We get SL to be 900 plus J 1786 kVA, right? So therefore, for the factory, the PL is equal to 900 kilowatts and the QL is 1786 kilovars. Right. Now, since the motor is added to raise the power factor, we know that the motor will be operating at a leading power factor. And for a leading power factor, SM is equal to PM minus JQM. All right. And PM was given as 100 kilowatts. So let us now look at the entire factory. So we put for the entire factory, this the power factor was raised up to 0.8. So we can find out what that angle is. Cos inverse of 0.8. And ST now is the total system, both the factory and the synchronous motor. So ST is equal to PT plus JQT. And PT would be the power from the factory plus the power from the motor. So that works out to be 1000 kilowatts. And then we can find out what ST is. We could have also used that relationship, this right angle triangle, to find out what QT is. So different ways of working it out. They all lead back to the same thing. So ST, using this relationship, would be PT over cos theta T. And since we have these values already, we can work out what ST is. And then we can find out what QT is by using Pythagoras theorem. ST square minus PT square. As I said before, you could have used tan of this angle being equal to QT over PT to find what QT is. So that's another way of working it out. All right. I think that was the way we probably taught it when we're doing the capacitor power factor correction using the capacitors. All right, so QT works out to be 750 kilovars. All right. Now remember that QT here is actually the resultant of the factory load minus the motor reactive. So the factory reactive power minus the motor's reactive power. Since they are going in different directions, the factory one is lagging, so it is pointing vertically upwards on the J-axis. For the motor, QM is pointing vertically downwards on the J-axis, so it's a minus J-axis. So if you sum the two of them, you will get QT. So QT is QL minus QM. So the sum is summing a negative number, right? So therefore, QM, which is we wanted to find out what the factory KVA, the motor KVA rating is, QM would be equal to the QL minus QT. And so therefore, substituting the values, QM is equal to 1036 kilovars. So writing now to come back to finding the KVA rating of the motor, SM is equal to PM minus JQM. So it is 100 minus J dot 1036 kVA. All right, so SM, when we were resolving it into polar values, we get SM is equal to 1040.87 kVA at angle minus 84. All right. So KVA rating by itself is 1040.872. You would probably round that off to 1041 kVA. And the power factor now will be the cosine of this angle, right? And since it is negative, we know that it is a leading power factor. So the motor is operating at 0.096 PF leading. All right. And again, since it's negative, the angle is negative, we know that it's a leading power factor. All right. And these diagrams, this is just to explain the diagrams. This is for the factory, A for the factory, B for the synchronous motor, and this is for the combined load. All right. So there are some questions here. I sent you this yesterday, so you would have the questions. So this is what we're going to be doing in the tutorial session. So I want you to start working on 3D and 3E. And we'll finish those for the tutorial session. 3F is a little bit more demanding in terms of what you're asked to do, not in terms of difficulty. So I know you probably would not be able to finish by 12 o'clock today. So I'm actually giving you 12 until 12 o'clock tomorrow. All right. So you can start working on this and we'll come back at around 10 o'clock to see what you have done with 3D and 3E. All right. Any questions? Any questions on what we have done so far?
Crystal clear.
Crystal clear. Okay. All right. That's good. That's good.
So I'll read up.
Oh, that sounds like Mr. Green.
Yeah, man. That's me. I'll read up and catch up and say what I need to say later on.
Okay. All right. Make sure you keep on top of the notes. If you read the notes and read the sections in the book that that you see where we have been looking at, you should be all right.
Yes, the book has been very helpful and just need to catch up on to where you are. I was doing some reading last night and I would like to submit some work to you and hear your views on where areas I need to focus on.
Okay. All right. I know I did promise to send back the labs last week, but I met up on a few personal challenges, so that wasn't done. But I have marked the two that have been placed in the Google Classroom. So you can, for those who submitted on the Google Classroom, you can check back to see the marking for it. I will finish the rest. So by tomorrow, everybody should get back theirs, and I will also send lab number 2. So you have probably about a week or so to do that. About a week, yeah. To do lab number 2. All right. So apologies for not sending them last week, but yes, as I said, I got caught up with some other stuff that kind of prevented me from focusing on those. All right. Any other questions, comments? If not, we meet back at 10 o'clock for looking at the tutorial questions. All right. So by the way, you can look at what we have done in this lecture notes to deal with those two problems, exercise 3D and 3E. Those what we have done today and from the notes should be able to help you with those. All right. All right. So I'll see you at 10 o'clock. All right. Bye, everybody.
My turn.
Okay. All right. Take care. 10 o'clock.